Okay, so thank you very much. Thanks for the kind invitation to be able to be here. I'll follow up a bit on what Per has been discussing. So I'll talk about quantum computing with superconducting circuits. And the people who are listed here is the current team working at ETH Zurich on this subject. It's not a small team anymore. We're maybe 25 or 30 students and technicians and staff working on this topic. And as Per said, this started out maybe 30 years ago, where scientists were doing maybe mostly experiments by themselves on these circuits, trying to understand how the quantum physics of them would work. And now there's also larger companies working on these questions, and there's also some collaborative research projects, one of which we have together with Per Delsing's lab here at Chalmers. So on this title slide here, you see you do see one of our devices. It's a superconducting circuit that we've designed at ETH and actually also fabricated at ETH. And it includes all these elements that Per has mentioned to you. It has superconducting circuits, it has microwave frequency resonators, and I'll tell you a bit how we use them. So therefore, I go a slide back here, where you see the chip in its full beauty. So all these kind of yellow structures that you see, there are 7 of them, one in the center here, and 6 other ones around it. These are superconducting qubits. These superconducting qubits we can control individually with microwave frequency pulses at frequencies which are similar to the frequencies that cell phones use to communicate with base stations. Then we can read out the state of these superconducting qubits, and for doing so, these yellow things here, and their size is about 200 microns or so across, are coupled to these microwave frequency waveguides that you see here. That's maybe a sort of about a millimeter long strip of wire that gets deposited on these chips. And then the qubits can talk to each other, do logical operations between them by being coupled capacitively through yet another microwave frequency resonator. And that's also something that Per had briefly mentioned. And when you're trying to do quantum computing with these structures, you're trying to make the quantum physics on these devices work the way you want by making the right chip, applying the right sequence of microwave frequency pulses to it, and in the end try to do it in a way to perform a meaningful calculation. And Per mentioned this Google quantum supremacy experiment, and I'll try to say a few words about that as well. Okay, so one of the things, so this is the current team working at ETH Zurich. So we've been at ETH since 15 years now or so, and there's a number of people who've helped us to get where we are. It's a big effort. Lots of people were involved. I'm thankful to all of them. It's also interesting to see what they're doing now. Like a good fraction of them is now professors at other universities. Apparently this seems to be an interesting field, so lots of people want to know about it and learn about it. And I think one of the requirements for making successful quantum computers, for bringing this from this kind of basic technology demonstration to a real largely used technology, it needs lots of people who know about quantum information science, who know about building superconducting circuits, and I mean that's maybe where you guys can contribute in the future, learn about this field and try to make the world successfully use quantum computers for solving difficult problems. So there's also some of our students now work at startups trying to build quantum computers, and at some of the big companies like Microsoft and IBM and others. So Per told you about the superconducting qubits and how they work. It's been something that people have actually started to try to do or tried to build these circuits in the 80s. And in the 80s, one did so mostly for studying the basic quantum physics of these circuits. But then when the ideas of quantum information processing and quantum computing came around, people got way more motivated to look at the physics of these devices. And now I think there's somewhere between 100 and 200 labs at different universities worldwide studying this physics. So it maybe did go from this exotic, hard-to-do thing in a few individual labs to something that is fairly widespread. And I think you've heard yesterday, for example, a lot about how to do quantum physics with atomic systems and photons. But you can as well do quantum physics at a similar level of quality with superconducting qubits and microwave frequency photons. And so one of the aspects that is also different now is that there now is quite a few industrial players trying to build superconducting circuits for quantum information processing. And here you see pictures of devices from Google, from Rigetti, which is a US-based startup, from Intel, and also from IBM. And so these companies now start to have sizable teams working on these questions. So I think any one of these companies has a few hundred people working on these subjects. And they're also they're starting to be concerned about protecting their knowledge about the devices. Yeah? And one of the ways how you can see that is that on the pictures that you see in the press now, is you mostly see the chips from the backside. Yeah? So the interesting qubits are on the other side of this chip, which faces this bigger chip at the bottom. And like with more academic work, you have still the pleasure to look at the front side of these chips, like I did on my title slide, and I'll try to explain you a bit more of how these work. So here's another picture of this device. I think maybe one thing that I should also say is that really the largest devices that people can make, companies or labs, have on the order of 50 qubits or so. And it's an enormous effort, even for a large company like Google and their team with maybe 100 people working on it to make these devices. So, it remains a large challenge to make devices with even more qubits, say with hundreds or thousands, or maybe in the end hundreds of thousands of qubits that you need to build a large quantum computer. And for many academic labs, it poses a challenge to make samples even with 10 qubits or so and make them work well. So what we are currently working on, and that's actually a device that we are doing experiments on as we speak. So this sample here that you see is actually in one of our cryogenic systems, and we explore its quantum physics. And the main use case that we explore for this is to correct errors that occur in quantum computers. Because errors occur in quantum computers all the time. Per mentioned to you that the fidelity of an operation is a key figure in describing the quality of a quantum computer, and you want to have that fidelity as close as possible to 1 or to 100%, you could say. And in a quantum computer, people are typically quite happy if they're at 99.9% fidelity. You could also, instead of talking about fidelity, you can also talk about the error. Yeah, 99.9% fidelity corresponds about a 0.1 to a 0.1% error, or to say a 10 to the minus 3 error probability. In an actual, like in a conventional computer, like in your cell phone or in your laptop or in this laptop that I have here on my desk, that presents this presentation, the error rate is 10 to the minus 18 or something like that. Yeah? So it's probably 15 orders of magnitude smaller than in these quantum computers currently. And that's one of the reasons why eventually quantum computers will need error correction. And I'll say a bit more about that at a later stage in this presentation. Okay, so I'll use this chip here as for illustrating some of the functionality that you look at in building a quantum information processor. So in our lab, we go ahead and we did go ahead and made a design for this device. Yeah? And as Per said, making this design typically involves essentially making a drawing of what this chip should look like and transferring that drawing to masks, from which using some photolithographic process, which is not so different from how you in the old days did photography, like exposing onto a kind of a photoactive material, this pattern that you see here, and then transferring it into your microchip. And so this is something that we do at ETH, students do in our lab, and they physically fabricate this device. And then once you have this device in your hand, and it's not that small, it's a few millimeters on a side, you mount it into a so-called printed circuit board that allows you to route the signals that you need to control the states of your quantum bits on your chip. And these signals, as I mentioned, are microwave frequency signals, so they get applied through coaxial cables, like a little bit like the cables that you use to connect maybe a signal source, say a radio frequency signal source, to your oscilloscope. So these signals get applied to these connectors here, and then they get routed towards the chip. And here's kind of, if you squint a little bit, you see that that's actually the chip that you've seen on the previous picture. And then, as Per mentioned, this chip then, to operate properly, it's a superconducting chip. So first it has to be cooled down to temperatures that are way below the transition temperature of the superconducting material. So that's in our case for the two materials that we use, niobium and aluminum. That's either around 10 Kelvin above the absolute zero of temperature, or about 1 Kelvin above the absolute zero of temperature. And so therefore you need to put these chips into a cryostat. And the PC board that you've seen before with the chip sitting there then gets mounted into this kind of metallic structure here, which looks a little bit like a puck, which is maybe something I know I'm a hockey player, so anything that looks like pucks is I always like. And then Sweden is also a country that is very much into hockey, so that's a sort of roughly a kind of a large puck size metal piece which holds the chip in the center. And in this package, we then cool down the whole thing in a cryogenic system. And so here you see such a picture. So luckily, our cryogenic system doesn't exactly look like that in our lab, but it's a bit of a photo montage so that you can understand better what needs to be done. So the chip actually sits at the bottom of one of these cans. One of the reasons why these quantum computer chips have pretty high probabilities of errors is that they're very sensitive to all sorts of things. Yeah? Disturbances like external electromagnetic fields from the microwave oven from somebody down the hall, or your cell phone, or the magnetic field of somebody's chair, or all these things, and those you have to kind of protect your quantum chip from. And therefore the chip sits inside a magnetic shield at the bottom of this cryostat. And as I mentioned, you need microwave frequency signals that control the quantum physics of the qubits on this chip. And these microwave frequency signals get applied through cables, and the signals you generate at room temperature. And one of the challenges is to how you actually make sure that you have an electronic chip that sits in one of these cryogenic systems at a temperature that is 10,000ths of a degree above the absolute zero of temperature. And nevertheless, you essentially take a metal cable and attach it to this cold chip and route the cable to room temperature. And so that's what's done in this kind of cryogenic system here. So the lowest temperature that you find in these systems is about 10,000ths of a degree at this metal plate here, about 1 Kelvin at this plate. There's about 1/10 of a Kelvin at this plate, about 1 Kelvin at this plate, and about 4 Kelvin at this plate, and 30 Kelvin at that plate, and then there's room temperature on top here. And for these different stages to hold their temperatures, it's built a little bit like in a sophisticated thermos bottle. So there's various levels of screening from thermal radiation built up in this cryogenic system, and this screening of thermal radiation you see here. So this is a photo montage. So typically when you see this system, you only see the vacuum can. So for example, when in all these press releases from IBM and Google and others, when they show you their quantum computer, mostly what you see is the refrigerator that they use to keep their chips cold. So that usually has a vacuum can, and then some radiation shield at 30 Kelvin, a radiation shield at 4 Kelvin, and a radiation shield at about 1 Kelvin. And this kind of onion-style setup to keep this device cold allows you then to operate a superconducting circuits at this low temperature. And as I mentioned, you use signals at microwave frequencies similar to those that are used in cell phones to control the states of the qubits, and therefore, like in these labs, what you see at Google, in our lab, at other places, is like a bunch of microwave frequency electronics that you then control with software to make the qubits on these devices do what you want. Okay, so I said a few words about this cabling here. Maybe I have a few more slides. And then if you think about what it's like to work in a lab on these types of things, you not only work on programming your computer, yeah? You also work on making everything around it work. For example, thinking about how you set the wiring up. Yeah? And like this, here's a picture of some of the wires that we've installed in this cryostat that go somewhere from a vacuum feed-through from room temperature through these different temperature stages somewhere to the lowest temperature where you then connect the qubit. And this kind of assembly is something that students in our lab designed and that then technicians fabricated and some student assembled and put into the cryostat, and that contributes to trying our quantum computer out in the end. So there's a few more kind of more detailed looks at the elements of that, and I think that's also when you're kind of a scientist working as an experimentalist on these things, yeah, that's something that you spend a lot of time with, like working on the practical elements of getting that to work and understanding how sort of the physics and the mechanical engineering that you need to do that relate to your goal of trying to make your quantum computer work. Okay, so I maybe have said most of that already. So here we're back at our chip. Let's maybe look a little bit more closely at one of the superconducting qubits. We'll pick the one in the center here. So I zoom a bit in, so it's a bit more convenient to you to see it. So the yellow structure is a superconducting qubit. Or the capacitive part of the superconducting qubit, and it connects through a Josephson tunnel junction. The yellow part is connected through a Josephson tunnel junction to this gray area, which you could call the ground potential of this electronic circuit. And so this is what forms the so-called transmon qubit. And this particular transmon qubit, it can interact with neighboring qubits through these bluish transmission lines. Yeah, and here you see one of these lines that I've mentioned before. A line is essentially a narrow, few micron wide superconducting metal wire that lies on your chip and that connects capacitively from one of these yellow qubits through this line. And this particular line then moves up to this other qubit. These two are now capacitively coupled to each other, and you can use this capacitive coupling to realize logical gates between the qubits. Okay, so what other parts do you have there? So there's like this purple line here. That's a microwave frequency line that allows you to change the quantum state of the superconducting qubit. Yeah? Initially, hopefully, your superconducting qubit is in a state that you would define as the ground state, in which you store the logical zero of your qubit. And to move this qubit from the ground state to an excited state, you would apply a microwave frequency pulse to it. And this is done through this microwave frequency cable here that then couples capacitively to this qubit. Then there is another, like a green wire that reaches the qubit, and this green wire we can use to apply a small current pulse to the qubit. And the small current pulse has the ability to tune the energy level separation between the lower energy state and the higher energy state of the qubit by applying a little magnetic field to the qubit locally. Because the magnetic field is generated at the end of this green wire, where the current is flowing, and locally a small magnetic field then shifts the qubit frequency. And that's a functionality that we use to mediate or to create 2-qubit gates. And I'll explain that in a bit more in a second. And then there's this red wire that connects to the qubit. And the red wire connects the qubit to one of these microwave frequency resonators that I've pointed out before already. So in this case, you see it here. It's this microwave frequency resonator. And this can be used to read out the qubit state. OK, so let's talk about these 3 manipulations, or the 2 manipulations, single qubit manipulation, 2-qubit gates, and the qubit readout briefly. So here's how you control the single qubit state. I said already you apply microwave frequency pulses to the qubit. So in a classical bit, you have just 2 states, a ground state and a first excited state. And the only thing that you can do is you can prepare it either in this ground state or like in a state 0 or in a state 1. And say in a classical memory element, these 2 states are distinguished, for example, by having a low voltage on your memory element or having a high voltage on the memory element. In a quantum computer, your qubit can not only be in a ground state and an excited state, but it can be in any superposition state. And therefore, you represent the quantum states of this qubit not as 2 states, a ground state and an excited state, but as all the states on the surface of a so-called Bloch sphere. And what you see here is a so-called Bloch sphere. And when the qubit is in a ground state, you can represent it as an arrow that points to the north pole of that Bloch sphere. And the excited state, it would be the south pole of that Bloch sphere. And the thing that is special in qubits in comparison to classical bits is that they can also be in superposition states. So this qubit state vector can essentially point to any point on the surface of this Bloch sphere, and all of these are valid states for the qubit to be in. And those we can prepare essentially by applying microwave frequency pulses to this wire here. We can, for example, prepare an equal superposition state. And if we double the length of that pulse, we can prepare an excited state. Or if we, again, double the length of the pulse, the qubit state vector will rotate from the north pole to the south pole and back up to the north pole and is back where it started. So that is how you do, how you write information into your superconducting qubit. And you can do the same thing about a different axis, this type of rotation of your qubit state vector. And you do so by changing the phase of the microwave frequency pulse that you apply to your qubit. And this is essentially everything you can do with a single qubit. You manipulate the single qubit state this way by applying microwave frequency pulses to your qubit. And here on the right-hand side, you actually see a way how to determine what the qubit is doing, and that's called state tomography for a single qubit. Okay, so an important aspect in these superconducting qubits is you need to be able to perform logic gates between them to implement any algorithm. And Per had briefly alluded to that and showed already a slide, and here you have a bit more detail. So there's 2 superconducting qubits here at the bottom. Each one of these qubits can either be in the state 0 or 1. And indeed, these superconducting qubits, they also have higher excited states, like 2, 3, or 4, as the number of excitations in the qubit. And for performing a logic operation between those, there's different things that you could do. And one of the things that we do in our lab is the following. So here's a qubit on the left, a qubit on the right. And the first thing that we do is we prepare both qubits in the excited state. So we apply a so-called pi pulse to the left qubit. That would bring us to this state here. We apply a pi pulse to the right qubit. That would bring us to that state. And so now both qubits are in the excited state. And now what we can do is we can use one of these green wires here to tune the transition frequency of one of the qubits down in energy by applying a small magnetic field. And so this is kind of visually shown here. So you could think about these states here as sort of shelves in a bookshelf. And now we've pushed the shelves on the left-hand side down so that the shelves on the left-hand side are aligned with the shelves on the right-hand side. And when that happens, then there's some interaction between qubit A and qubit B. And this interaction actually allows us to now shift the state from 1, 1 to 2, 0. Yeah? It's sort of these 2 qubits can interact with each other. And then maybe in my shelf picture, you could shift a book over from the right side to the left side and back to the right side. And that is the mechanism that is used to create a logical 2-qubit gate in superconducting circuits. And there's actually an interesting phenomenon that makes this work that I probably don't have enough time to explain in detail to you. But this kind of mechanism, like this tuning qubits into resonance with each other through small applied magnetic fields, is what initiates 2-qubit gates in these circuits. Okay. So you can write this down in terms of, you can do the math for it and write down some unitary matrix that describes it, but I think I won't discuss that in more detail in today's presentation. And you can also ask yourself, how well do these gates work? And as Per said, if you are careful, these gates can work with fidelities of 99% and maybe above, but they're still way worse than any logical operations that you would do on a classical computer. So then the last element in a quantum computer that you need is you need to have some qubit measurement capability. And the measurements get done by coupling the qubits to these microwave frequency resonators that you see in red here. So here you see an optics analog of such a microwave frequency resonator. An optics analog is a system made of or an optics resonator is typically one where you have two mirrors at a certain separation from each other. And these two mirrors allow for a certain optical mode to be stored between the two mirrors. So it has some resonance frequency that has to do with the separation of the two mirrors, the propagation velocity of electromagnetic radiation, and the volume between the two mirrors. And the superconducting qubit that sort of couples to that mode, that shifts the resonance frequency of that resonator. So you can think about it as if you would insert a little piece of dielectric material into that resonator. And when the qubit is in the ground state, that dielectric material has one dielectric constant, and if it's in the excited state, it has a different dielectric constant. So what this does, it does change the resonance frequency of the resonator. And so here you see resonance curves of such a resonator when there's no qubit in the dashed curve here, when the qubit is in the ground state in the blue curve, when the qubit is in the excited state in the red curve. And so now if you would measure the resonance frequency or the transmission through that resonator when the qubit is in the ground state and you choose this frequency here, you would measure high transmission. And then if your qubit is in the excited state, you would measure low transmission. And that's the way how in all these superconducting qubit systems that are used for quantum computation, the qubit state is read out at the end of a computation. And there's different ways how you could do that. You could measure either the transmission amplitude or the phase of the transmission. And you can also do the math for that, which I will not discuss now. What is then interesting is that this really works even though you have a quantum system. It's a superconducting qubit on a chip. You can perform this measurement in a single shot. Yeah? You could prepare a superconducting qubit either in the excited state or in the ground state, measure once, and know exactly whether that measurement was realized. And so, for example, if the qubit is in the ground state, you would measure one phase of the transmitted microwaves. If it's in the excited state, you would measure the other phase. So here you see such a measurement. The qubit is in the ground state. You switch on your probe tone, and you see, okay, your signal has one value, a negative value. And if the qubit is in the excited state, you get another signal that shows that a positive signal that indicates that the qubit is in the excited state. And you can distinguish these two states from each other very easily and with high fidelity. And these are essentially the elements that you need to operate a quantum computer. Single qubit gates, 2-qubit gates, readout. And these elements have been developed, say, through the last 15 years or so. And now they get put together to work to realize quantum information processors. And so here's a list of things that have been done in these superconducting circuits. And up until recently, sort of all these basic elements have been put to work to realize really basic quantum algorithms or demonstrations of little quantum algorithms. And maybe the thing that really got everyone excited a lot was this Google quantum computational supremacy experiment. And I mean, one of the measures how you see whether people are excited is does this scientific result make it into the news? Yeah? And both in Switzerland and in Germany, where I checked, this result from Google was it made the sort of the evening news. Yeah? It was on the front page of the evening news web page. So people were really excited about it. So why is that? And what did Google do? So here you see a picture of a device, a very schematic picture of a device that Google made. So every one of these crosses is a superconducting qubit. There's 53 of them. There was a 54th one here, but that didn't work, unfortunately. So even Google is not perfect in that sense. And what you then see on this picture here is like there's a little color code for the errors occurring on the qubits. And there's the qubits are the crosses, and the boxes between the qubits are the elements that are used to do gates between two neighboring qubits. And one of the things that was really amazing about the Google work is that they managed to have every single element on this chip with 53 qubits, and even more coupling elements between the qubits work really well at the current state of the art. So here's a plot about the errors that occur on this chip. And essentially everything that you see on their device works better than with a 1% error. And as I said, if you look at classical computing, where everything works better than 10 to the minus 15 error, this sounds not so great yet, but this is the very best that anybody has ever done in the world. And the interesting bit about it is that now with such high quality chip and control, they could actually challenge classical computers. And the way how they try to challenge the classical computer, they try to run the most complicated set of gates that was possible on this set of qubits. And so here you see, again, a picture of this arrangement of superconducting qubits with their couplers. And this is a sequence that labels the number of qubits this way and the number of gates that way. And what they were trying to do is to have at least as many gates in sequence applied to the qubits as they had number of qubits on their device. And what that then allows them effectively is to have every qubit on the chip interact with every other qubit on the chip at least once. And to do so, they chose to, instead of implementing, say, an algorithm that would calculate the answer to a specific question, they chose to implement a set of random gates on their 53 qubits. And the advantage of this set of random gates is that the set of random gates creates a very complex 53-qubit quantum state. And this 53-qubit quantum state, as Per said, requires 2 to the 53 a size of a Hilbert space to fully describe it. And exactly that is very difficult for a classical computer to calculate. And what they then did do, they came up with some benchmark. So they ran their quantum computer, and they ran the biggest classical computer that they could get a hold of, and compared the results of their quantum chip to the results of their quantum computer, and asked how close are they to each other. And how much time did it take both the quantum computer and the classical computer to find that result. With the time that they were willing to spend on the classical computer, they essentially stopped at having this large high-performance computer run for 5 hours on a job that took their quantum computer, say, only a few seconds to solve. And in the end, they extrapolated that result to even more complicated sets of gate sequences and showed that their quantum computer with a set of random gates could calculate something that would be hard or close to impossible to do on a classical computer. Okay, so it seems that I'm a bit slower than I thought, and for not going over time, I think I'll wrap it up here. I hope that I've been able to tell you a bit what the elements are in a superconducting quantum computer, how they work, what parts you need to put together to run it, and I've told you a few more words about what Google has done in their Google Quantum Supremacy experiment. And I think it's really an exciting time to work on superconducting qubits. So there's lots of challenges remaining to work the bugs out of your superconducting qubits. That's maybe where you guys can contribute. So you can design and integrate quantum circuits. Developing processes for actually making them is important. As Per said, selecting the right materials is important. Working on the electronics and the cryogenics of these systems is something that you could do now and in the future to make this field move forward. Working on software for control and automation. And so overall, I think we've seen this transition not only from the first to the second quantum revolution, but maybe also from exploring quantum physics to exploring quantum engineering, where you try to use quantum physics to build useful tools for the future. Okay, thank you very much, and I'd like to thank you for listening and our team for their contributions.